Binary number systems, part 1. Let's begin by looking at the decimal number system. The decimal number system is a base 10 number system. This means that the digits used when we write down decimal numbers are between 0 and 9. Remember that the 10 is not a digit, it's not a single digit, it is combined is made up of 2 digits. The decimal number system is a positional number system, which means that the weighting of each digit is 10 raised to the power of the digit's position. We count digits' position from 0 upwards, beginning on the right hand side of the number. So in the 0th position we have the weighting is 10 to the power 0. In the first position it's 10 to the power 1, second position 10 to the power 2, 10 to the power 3, and so on. Don't forget 10 to the power 3 is 10 times 10 times 10, or 1000. 10 to the 2 is 100. 10 to the 1 is 10. And by 10 to the 0, 10 to the 0 is 1. So here's our decimal number. And the digit on the left hand side, or in the most significant position, stands for 3000. The 4 stands for 400, the 6 stands for 60, and the 2 just stands for 2 units. So the total value of that number is 3462. Now if we apply the same idea to the binary number system, which is a base 2 number system, it's also a positional system. We have the following. We have the 0 position is weighted 2 to the power 0. The 1 position is weighted 2 to the power 1. The second position is weighted 2 to the power 2, and so on. And don't forget that 2 to the power 3 means 2 times 2 times 2, or is 8. 2 to the power 2 is 2 times 2, or 4. 2 to the 1 is just 2, and 2 to 0 is 1. So here's a binary number. Notice that binary numbers can only use the digits 0 and 1, because if we've got the base is 2, we can only use numbers up to, or digits up to 1 less than the base. So we can only use the digits 0 and 1. And the 1 on the far left hand side, or in the most significant position, is weighted 2 to the power 3, so that's 1 lot of 8. The number in the second position is 2 to the power 2, or 4. In the position 1 there is no digits, or it's the digit 0, so that doesn't give us anything, and that leaves us with just 1 in the least significant bit position of the number. So the total value of this binary number is 13. Right, counting in binary. Let's count in binary from 0 up to 16. And as you can see from this table, the column on the right hand side, or the least significant bit position, is weighted 1, or 2 to the power 0. The next significant position is weighted 2. The next significant position is 4. And the most significant position on the far left hand side is 8. So 0 is when all the digits are 0 and there's no value of 0. 1 is when we have 0, 0, 0, 1. Now to get to 2, we want a 1 in the 2 column, so, and 0 everywhere else, so we get 0, 0, 1, 0. To get 3, we want a 2 plus a 1, so we want 1 and a 1 in the 2 least significant bit positions, and zeros everywhere else. And proceeding in this way, we go up through this table to get the first 8 digits. 8 digits counting from 0 up to 7. So this is 0, 1, 2, 3, 4, 5, 6 and 7. Right, and you'll see that as we've counted up from 0 to 7, that the least significant bit column has gone 0, 1, 0, 1, 0, 1, as we found before when we looked at truth tables for switches. The second most significant bit position goes 2 zeros, 2 ones, 2 zeros and 2 ones, and the third significant bit position goes 4 zeros and 4 ones. So we've actually, in the first 8 rows of this table, we've written down every possible combination that we can get with 3 binary digits. This is every possible combination. As we come to the next number in our sequence of counting, which is number 9, the 8, we now go 1 to take us from 7 to 8. So suddenly we now start adding digits to the most significant bit position, because we're dealing with a 4-bit number. So 8 is represented by 1000, 9 is 1001, 10 is 1010, because that's an 8 plus a 2, that gives us 10, and so on. And you can see that the pattern that we started when we went through the first 8 rows continues down through this table. So that's how we count in binary. So just to recap, the least significant bit column goes 0, 1, 0, 1. The next most significant bit position goes 2 zeros, 2 ones, 2 zeros, 2 ones. Then 4 zeros, 4 ones, 4 zeros, 4 ones, and finally in the most significant bit position, 8 zeros and 8 ones.